Hello friends, welcome to my YouTube channel Physics Ki Pathshala. Today I am going to teach you a topic from chapter Magnetic Effect of Electric Current, and the topic's name is Force between two infinitely long parallel current carrying conductors. So let us see. Alright, we have two conductors 1 and 2 carrying currents I1 and I2 respectively. Now this is the case of like currents. The meaning of like currents means the sense or the directions of the currents should be same in both the conductors. So in the picture we see I1 and I2 both are traveling or both are flowing from bottom to top, means they are having the same sense of direction. Now let us say the distance between the two conductors are capital R. You will find this labeling with the small letter A, S, D or Z in different textbooks depending upon the different authors. So that doesn't matter, you can label it with any letter of your choice. Alright, so before we start the derivation of it, let us understand few things. We know that if we have a conductor having a current, then it generates magnetic field around it, and the direction of magnetic field can be understood with the help of right hand thumb rule. So I explain that first. So let us say this is the conductor, say for example conductor 1. I am holding this in my right hand. So I come here, I am holding this in my right hand. So if I hold the conductor like this in my hand and the thumb, this thumb represents the direction of current. You see in the picture also, thumb is upward, current is upward. Then this curled finger, these curled fingers should represent the direction of the magnetic field around it. So if we see, this is the thumb, current is upward, then the curled fingers are representing the direction of magnetic field around it. So here we see, if I am closing and curling my fingers, then on the left of the conductor, fingers are coming out of the board, and if I go on closing like this, then on the right it is going inward to the board. Understood? Now if you see this second conductor lies on the right of the first conductor. So for second conductor the field will be inward to the board. Of course, you see from the picture it is very clear that second conductor is kept around the first conductor, and around the first conductor there is magnetic field, means second conductor is in the magnetic field of first conductor, and for second conductor the direction of magnetic field should be inward to the board. And since the second conductor is in the field of first conductor, so I have written over here B1, that is magnetic induction due to first conductor. Likewise you see second conductor also carries some current, so according to right hand thumb rule, the magnetic field around it will be anti-clockwise, and when we are curling my I am curling my fingers, this curled finger, then on the left the fingers are coming out of the board, and on the left first conductor lies. So for first conductor the sense of magnetic field or the direction of magnetic field should be coming out of the board. Alright, so I have drawn this B coming out. Now I have labeled this as B2 because this is the magnetic induction due to current in the second conductor. This much is clear, I hope. Now we also know that when a conductor is kept in the magnetic field, it experiences a force. So both the conductors are kept in two separate fields. So both the conductors should be experiencing two separate forces. So let us understand where will be the direction, how will be the directions of those conductors be. Alright, so one by one we will see. Now to find the direction of the force due to magnetic field, we need to have the knowledge of something called Fleming's left hand rule. So Fleming's left hand rule says that if we stretch our these three fingers of left hand, that is first finger, middle finger and thumb, like this perpendicularly to each other, then first finger represents the direction of magnetic field, middle finger represents the direction of current, and thumb represents the direction of force. So for first conductor, if I orient my left hand according to the diagram, so let us see. current is upward, so my middle finger should be upward. Magnetic field is out of the board, so my first finger should be out of the board, means towards your screen. I have oriented according to the requirement. So you see, my thumb is representing towards the right, and this represents the direction of force. So the force has to be towards right, and since this is the force acting on first conductor, so I have labeled it with F1. So this is very simple. This is now likewise for second conductor. If I go, so I stand over here, I orient my finger according to the requirement. You see the current is upward, so middle finger has to be upward. So okay, fine, upward. Magnetic induction is into the board, so first finger has to be into the board. I move like this, it is into the board, so this thumb has to represent the direction of force, which is towards right. You see, the force has to be towards right. Now this force is acting on second conductor, so I have labeled this with the letter F2. So we understood this, the directions of F1 and F2. Now you see in the picture, F1 and F2 are acting towards each other. What does that mean? That means these forces are attracting in nature. Alright. So this much we understand, that we have two conductors carrying currents in the same direction, then they will attract each other with some forces. Now let us calculate the formula for the force. Now before that, we need to find the magnetic induction, because I write the formula for force. We have learned in previous class that the formula for force acting on a conductor of length L and carrying a current I through it is given by this formula: I B L sine theta. This is the general formula for force. Now to calculate this, we need magnetic induction. So hence we first calculate magnetic induction. Now one more thing I would like to share over here is this theta is the angle. Theta is the angle between magnetic induction B and the length. Now you see, take the example of any conductor. Conductor is kept like this, so the length will be upward. And magnetic induction, for this magnetic induction is out of the board, so like this, out of the board. Now how much is the angle between them? Is 90 degree. Likewise for second conductor, length is upward, it is kept vertical, upward, downward, whatever you can say, no problem, it is vertical. And the field is inward. Inward means inside the board. Again it is 90 degree. So the directions or the angle between them is, so theta is the angle between L and B and L, which is nothing but theta is 90 degree. Therefore the formula for force in our case has to be I B L. So this we have to remember. Call this as equation say A. Now according to Biot-Savart law, we have learnt in our previous class, Biot-Savart law, I write it BS law. According to BS law, the derivation for B, that is magnetic induction, in general, the formula for B is mu naught by 2 pi. How much it is? Mu naught by 2 pi I upon the distance between the conductor and the point of observation. So that distance you will find different in different text. In general, it is written with the small letter A or D or S or Z, anything. We have written it with R. So this is the general formula. In our case, therefore for our case, B1 and B2 can be written as, if I write B1. So B1 is the magnetic induction due to first conductor. So it will be mu naught and current flowing in first conductor, because B1 is the field due to first conductor. So this is 2 pi. Distance between them are R. And likewise B2 can be written as what? It is the induction due to second conductor. So the current in second conductor we have to take I2, and then 2 pi, again the distance has to be same, that is R. So B1 is mu naught I by 2 pi R and B2 is mu naught I2 by 2 pi R. So if we put the value of V1 and V2 in this formula A, we will have the formula for F1 and F2. So we can write, so therefore F1 is the force on first conductor. So current through the first conductor, that is I1. Now B, here B is the magnetic induction in which the conductor has been kept. So first conductor has been kept in B2. So here I will write B2. And then length of this conductor, even though we have taken the conductor to be infinitely long, but infinity is not practically possible. So we consider some very long length, say L. Alright. So we substitute for B2 from here. So this is I1. In place of B2, I will write mu naught I2 by 2 pi R and then L. Alright. So in textbooks you will find that they ask you to find the derivation for force per unit length. So divide by length. So force per unit length, no problem. You find force or force per unit length, no problem. F1 by L you will write. So this will be mu naught. You write I1 and I2 all together, that is I1, I2, put it in bracket if you want, and then 2 pi R. So this you got the force acting on first conductor. Now for second conductor you write F2, again the same formula, here the current has to be in second conductor, that is I2. Magnetic induction should be the induction in which the conductor is kept. So second conductor is kept in the induction due to first conductor, that is B1. So over here you will write B1 and then length, of course. So I2, in place of B1 we will write this. That is mu naught I1 upon 2 pi R and then length. Again we will take length on the left hand side to have the formula for force per unit length. So what we are left with is mu naught by 2 pi R, of course, and then we will write this I1 and I2 all together again in the similar way. So what do you see? These two formulas. What do you see in these two formulas? Both the formulas are same, F1 and F2. You see the right hand sides are same in both the equations. That means both the conductors will experience same force. So we see that the right hand sides of these two equations are same. Means both the conductors will be experiencing same amount of force and towards each other. So in place of writing F1 and F2 separately, we can write a common force for them. We can say that the two conductors having like currents flowing through them will experience an attracting force. Say F. In place of F1 and F2, now we will write F on F upon L, that is force per unit length, which is equal to 2 pi mu naught by 2 pi R I1 I2. So this is the case for like currents. When you have two parallel conductors kept at a distance R, separated by each other and having currents flowing in same directions, experience attracting force having magnitude mu naught by 2 pi R I1 and I2. Now what will happen if you change the direction of current in one of the conductors? So that will be the case of unlike current. Here we have written like currents. So that will be the case of unlike current. So this is very obvious that if you change the direction of current in the two conductors, then the directions of magnetic field and forces will also change, and that you can understand with the help of thumb rule and Fleming's left hand rule, that the forces will now be acting like this, means opposite to each other and outward to each other. What is the meaning of that? The meaning of that is the two conductors will now be repelling each other in place of attracting. But nevertheless, very important to understand is magnitude of the force will still be same, because In case of unlike currents, you are only changing the direction of the current. You are not changing the magnitude of current, and hence the magnitude of B and magnitude of F will remain the same. So I hope you have understood this topic of the forces acting between two parallel conductors in case of like and unlike currents. So if you have liked and you have understood this topic, then please like, subscribe and share my video with others also. Hopefully in coming days I will come up with some other topic of physics. Till then, take care of yourself. Have a good day. Thank you.